Welcome to this lecture series in number theory. So far we have only done what I call modular arithmetic, or what is I think generally known as modular arithmetic, which is something that we have recalled so many times. The things have been pretty simple, but now things will get somewhat more difficult. We are starting a new module, and now the things will be more sophisticated, at the same time much more interesting than before. All right. So here are some puzzles for practice. And now let us get started. So suppose we have a natural number n and we have some integer a. So there is a very fundamental question that we can ask, which is that can we find an integer x such that this congruence holds? And this may seem like a question coming out of nowhere, but soon we will see that this question is of fundamental importance. And by soon, I mean probably not today, but in the course of the next few lectures. But at any rate, this should feel like a very interesting question. We are asking a very simple question. When can you solve this equation? This congruence equation. This is not a usual equation. This is a congruence equation. So, is the answer always yes? Can you always find such an integer, or is the answer always no? Let's see. Let's understand this via examples. So, in the first case, can we find an integer x which satisfies this? Well, clearly we can, because you can just substitute x equals I don't know, x equals what? 4. X equals 4 works. So this one has a solution. What about this guy? This, I claim, does not have a solution, and the most brute force way to see this is try all the 6 possible options. So you can try x equals 0, x equals 1, x equals 2, and so on. And in each case, you will see that never this congruence will hold. So the answer is not always yes, and it is not always no. So when is it yes and when is it no is a question that we will formally frame. But before that, here is the definition that we can make now. So given a natural number n and an integer a, we say that an integer b is an inverse, and I say an inverse, of a modulo n. This is a, not a. This a is that a. So we say an integer b is an inverse of a modulo n if this congruence holds. And the terminology is coming from our usual definition of inverse in, let's say, rational numbers. So suppose we are given some rational number q. What is the inverse of q? The inverse of q is another rational number, call it whatever, L, such that this happens. This is exactly the definition of the inverse. We write it like 1 upon q, but the definition is something that satisfies the equation that I wrote. In rationals, every non-zero element has an inverse, but in integers, no. In fact, most integers do not admit an inverse. However, in congruences, when we are talking about congruences, the situation is not so simple. The answer is not so straightforward. For the rationals, very simple answer. Everything but 0 has an inverse. For integers, also very simple answer. Only 1 and -1 have an inverse. Every other number is devoid of an inverse. For real numbers, also very simple answer. Every non-zero element has an inverse. Complex numbers, same thing. But in congruences, when you are working modulo n, the answer is not so simple. And yeah, so this equation is very, very similar to the congruence equation. There's a 1 on the right side, product of 2 things on the left side. So I hope the terminology is sitting well with you. And it will behave a lot like the inverses that we see in usual numbers. But that will take some time to digest. Today's lecture is not sufficient for that purpose, but we will get to it. So here is the basic question that we want to ultimately answer, not in today's lecture, but ultimately. Can we characterize exactly when an integer a has an inverse modulo n? Meaning, just by looking at a and n, can we come up with a test or some criterion, some classification which tells us immediately if we can find an inverse? The process of finding an inverse and coming up with the exact inverse, or at least one inverse, is a separate question. Here we are just asking for a characterization which guarantees the existence of an inverse or tells us that there cannot be an inverse, the perfect characterization. And yes, such a characterization does exist, a very satisfactory characterization does exist, but we will discuss it in subsequent lectures. Today we want to explore this concept a little bit and prove some very basic properties about it. So, the best way to understand a concept is by playing around with it in some rich examples. It's a secret in mathematics that examples are probably the most important things. We are led to believe in usual coursework that theorems and proofs are most important. But I would say that playing with examples is even more important. It is what builds intuition, and it is these things that lead to theorems ultimately. Now, I don't want to give a statement set in stone here, but still, it's a meaningful statement. So anyway, so suppose we have fixed an n, and now let us play around with various a's. To start with, we will use a equals 2 and try to see if it has an inverse modulo n. So what is the equation that we are trying to address or trying to understand? We are trying to see if this equation has a solution. Right? This is the equation that we are worrying about. So as we substitute values of x, we want to see if this will ever be satisfied. So let's start with x equals 1. If we substitute x equals 1, where are we? And yeah, so before I proceed, I have listed out all the possible remainders that you can get when you divide an integer by 8. Right? These are the 8 possible remainders that you can get. So we want to see if this can be ever satisfied. So let's start with x equals 1. If you substitute x equals 1, what does 2x become? 2x becomes 2. And the remainder that 2 leaves when you divide it by 2 is 2. So we start here. Basically, this 2 is our starting point. Now we substitute x equals 2. So the left side becomes 4. But let's think of 4 in this way. We were at 2, which was 2 multiplied by 1. To go to 2 multiplied by 2, we just need to add a 2 to it. So many 2's in that statement. So if you add a 2 to 2, you will go to 4. Right? 2 into 2 is 4, but I want to think of it as adding a 2 to 2. Right? So we kind of move to 4 in the next step. That's how I want to think about it. Now we are at 4. And which we obtained by substituting 2 in place of x. But now let us substitute 3 in place of x. And again, instead of thinking of it as 2 times 3, let us think of it as this number, which is 4 plus 2. This thing is 4 plus 2. So we were at 4 currently. Plus 2, we will move to 6. So to record all the remainders that you obtain as you substitute the values of x, all you need to do is just keep moving by steps of 2. Next time if we move with a step of 2, we are adding 2 to 6. We get 8, but we are only interested in remainders. Right? 8 is nowhere here in this list because we are only interested in remainders. So 6 plus 2 is 8, but modulo 8 it is same as 0, so we move to 0 after that. And now again, if we add a 2, we come back to 2. And therefore we will keep moving in this cycle. We will never reach 1, and therefore this congruence cannot be solved. This congruence has no solution is all that I want to say. Right? If you keep substituting the values of x, you will keep moving in this cycle. Okay, let that sink in. Let's see more examples. This time, we have a equals 3. So the congruence we are worrying about is, we are trying to see if this has a solution. Like in the previous one, we will start with substituting x equals 1. So we are currently at 3. We are starting at 3. X equals 2. When we substitute x equals 2, that is 3 times 2. But again, as in the previous one, we will think of it as moving 3 steps ahead. We are currently at 3. We are moving 3 steps ahead, so we will reach 6. So we start with 3, we go to 6, then again 3 steps ahead. 6 plus 3 is 9, but 9 is same as 1 modulo 8, so then we will go to 1. Right? Another 3 steps, we will go to 4. 4 plus 3 is 7. 7 plus 3 is 10, but modulo 8, that is same as 2. And 2 plus 3 is 5. 5 plus 3 is 8, which is 0. And 0 plus 3 is 3. So we are back at 3. But anyway, we did not need to trace out all the things. We reached 1 is the point. We started with 3 by adding 3. We, in fact, in the second step, the 3 times 3. This was 3 times 1, then 3 times 2, then 3 times 3. That is our solution. So 3 times 3 is congruent to 1 modulo 8. So we do reach 1 is the point, but still I traced out the entire thing. Let's do more. A is equal to 4. So we are starting at 4. Again, let me write down the congruence that we are trying to study. And yeah, let me also mark it. So here we do get a solution. Here we get a solution, but here we don't get a solution in the first case. So now we are here. We start at 4. We add 4, we get to 0. Because 4 plus 4 is 8. 8 is same as 0 modulo 4. You again add 4, you come back to 4. So maybe I should draw it like this. You add 4, oops. So we will keep running in this cycle and never reach 1. Okay, so here we don't get a solution. Let's do more. A equals 5. Start with 5, add 5 to it. So 5 plus 5 is 10. 10 is same as 2. 2 plus 5 is 7. 7 plus 5 is 12, which is 4 modulo 8. 4 plus 5 is 9, which is 1 modulo 8, and we have reached 1. So we have a solution to this. 5x congruent to 1 mod 8. We have a solution to this. But let me trace out the entire thing. 1 plus 5 is 6. 6 plus 5 is 11, which is same as 3. 3 plus 5 is 8, which is same as 0. And 0 plus 5 is 5. Very similar trajectory that we observed here. What's going on? Not lastly, but at least let's do this. A is equal to 6. Let me just draw it out, and I encourage you to maybe pause the video and draw these for yourselves. So you start with 6. Then you go to 4. Then 2. 0, and then back to 6. No solution, because you never reach 1. Very similar trajectory to the one with 2. What's going on here? A equals 7. So start with 7. Then you go to 6. You go to 5, 4, and so on. You do reach 1, so you have a solution, but let me complete. Great. So I hope this example at least turned some gears in your head. We'll do more examples. This time we have taken n as 15, a as 2. Let's see what happens. So our congruences, like in the previous page, we start our journey at 2, then we keep adding 2. (14 plus 2 is 16, which is same as 1 modulo 15. And yes, therefore we do reach 1 and we have a solution, but let me complete the trajectory. Great. Next, a is 3. Start at 3, then keep adding 3. 12 plus 3 is 15, which is same as 0. And we see a cycle. We see a cycle which doesn't hit 1, so there is no solution. A equals 4. Start at 4, keep adding 4. 12 plus 4 is 16, which is same as 1 modulo 15. 17 is same as 2. 14 plus 4 is 18, which is same as 3 modulo 15. And we see that we did reach 1 at some point, so the congruence does have a solution. This time a is equal to 5. Start at 5, keep adding 5. And very soon we are trapped in a 3 cycle, so there is no solution. This 3 cycle does not visit 1, no solution. A is equal to 6. Start at 6, keep adding 6. Trapped in a 5 cycle, which does not visit 1, no solution. Just last one, a is equal to 7. So the congruence is 7x congruent to 1 mod 15. Start at 7, keep adding 7. 14 plus 7 is 21, which is same as 6 modulo 15. 13 plus 7 is 20, which is same as 5. Yeah. Beautiful shape has emerged. So this has a solution, of course, because it visited 1. Okay, try to conjecture, try to come up with a pattern. What is going on? What could be the explanation for sometimes the solution being there, sometimes no solution? Okay, so this was just for some hands-on practice, and now let's prove some basic facts about inverses. So a question arises, if there is an inverse, how many are there? We have seen that there may be no inverse, but there could also be, depending on what a and n are. So if there is an inverse, how many are there? It's a silly question if one poses it like that. For example, suppose you have found an inverse. Suppose this happens. A was given to you, and suppose you found a B such that this happens, then this will also be true. This is also true, or yeah, this is true for each k. No matter what k you plug in, this congruence is still true because this is congruent to 0 modulo n, so it kind of just evaporates. It doesn't do anything. So as soon as you have one solution, one inverse, you have infinitely many inverses. So that's like a silly answer. But modulo n, the inverses are unique. So what we are trying to say is, if A has an inverse modulo n, then it is unique modulo n, meaning if you have two inverses, suppose B and B prime are two inverses. So let me write down the precise statement, what I mean by unique modulo n. So that is, if B and B prime are inverses of A modulo n, then they are congruent. In the eyes of n, they are the same. So in that sense, they are unique. Okay? The proof is not difficult. So suppose not. So suppose B and B prime. So assume that A admits two incongruent modulo n inverses. So two incongruent inverses modulo n. That is, we have B and B prime such that AB is congruent to 1 mod n, AB prime is congruent to 1 mod n, and B and B prime are incongruent, so B is not congruent to B prime modulo n. Suppose this happens, we want to produce a contradiction. So from the first two, this is 1, this is 2, and this is 3. So from 1 and 2, or maybe I'll make it simpler. So from 1, I'm just restating 1, we have AB is congruent to 1 mod n, but now we multiply by B prime on both sides. B prime AB is congruent to B mod n, which shows AB prime times, sorry, this was a B prime. So once again, what did I do? I multiplied by B prime on both sides. So here I get B prime AB, and here when I multiply by B prime, I get a B prime. So now, instead of writing B prime AB, let me write it as AB prime times B, congruent to B prime modulo n. And now use 2. Using 2, AB prime is congruent to 1 modulo n. From 2, we get B is congruent to B prime modulo n. So there was really no need to use contradiction. We could have just said let B and B prime be inverses of A modulo n. We would have these two equations, and this reasoning would have shown that B is congruent to B prime modulo n. Going by contradiction has just made it a little more convoluted than it needs to be. Anyway, the reasoning is very, very simple, so I don't want to spend more time on it. But it is an important observation that if an inverse exists, it is unique modulo n. There is at most one inverse modulo n. Okay. Now finally, we will prove various equivalences. So as usual, fix a natural number and some integer a. Then the following are equivalent. So there are some 5 statements. All of them will be proven to be equivalent. And the way we will do it is, we will show 1 implies 2, 2 implies 3, and so on, and 5 implies 1. So what is 1? 1 is that A has an inverse modulo n. This is the first statement. The second statement is that if you have something that is not modulo z, I have written but I meant modulo n. If you have something which is not divisible by n, and you multiply that with A, you get something that is not divisible by n. So we are saying that 1 implies 2, and we are also saying that 2 implies 1, but we will actually not go that way. We will just keep coming down, and then ultimately show 5 implies 1. So for now, let's just show that 1 implies 2, and let the statement be very clear. So proof of 1 implies 2. So so from 1 there is an inverse. So from 1 there is some integer b such that ab is congruent to 1 mod n. Now if ay is congruent to 0 mod n, so we wanted to prove 2. It suffices to show, or it is equivalent to show, that if this happens, then y is necessarily divisible by n. Right? To prove 2, we just need to show that whenever ay is divisible by n, y is also divisible by n. So if ay is divisible by n, meaning ay is congruent to 0 mod n, then multiply by b on both sides. Right? We just multiplied by b on both sides. But a times b is congruent to 1 modulo n. That's how b was chosen. So that gives y is congruent to 0. Basic modular arithmetic. Very simple. Okay, next. If x and y are mutually incongruent modulo n, then ax and ay are also mutually incongruent modulo n. So we want to show that 2 implies 3 this time. So to do that, suppose ax is congruent to ay mod n. We want to show that x is congruent to y modulo n. That will prove 3. We are given 2, we will use 2. So from this we get ax minus ay is congruent to 0 mod n, which we can write as a times x minus y congruent to 0 mod n. But now using 2, we just immediately get that x minus y is congruent to 0 mod n, which shows x is congruent to y mod n. So this proves 3. Okay. Proving 4. We will prove 3 implies 4. What is 4? 4 says that for each integer b, there is some x for which this holds. Right? Okay, so this is probably the most interesting one. This implication, 3 implies 4, is probably the most interesting one. And here is what we will do. Fix a b, and we want to show that this congruence can be solved, meaning there is some integer x for which this happens. Okay. Now b leaves some remainder modulo n. So there is no loss in assuming that b is in this range. So keep that in mind. Like, we can assume we are working with remainders. This whole congruence business is the algebra of remainders. So every integer modulo n is just a remainder modulo n. Okay, fine. So my point is, consider these numbers. Consider a 2 times a, or maybe I should write a times 2, a times 3, up until a times n. So these are n integers, n genuine integers. But using 3, instead of writing a, let me write a times 1. And in fact, maybe I will make them with a separate color for emphasis. So all these numbers 1, 2, 3 up to n, they are pairwise mutually incongruent modulo n, right? 1 and 2 are not congruent modulo n, right? So I'm making a very simple statement. I'm saying that if I and j belong to this set and I not equal to j, then I is not congruent to j modulo n. It's a very simple statement. Think about it. So using that, we know that these are pairwise mutually incongruent. Now using 3, we know that therefore these numbers, the numbers that have been written, they are also pairwise mutually incongruent. That is exactly what 3 says. 3 says that if you have two numbers which are incongruent modulo n, then if you scale them by a, you retain the incongruence. So these pink numbers that are written here, they are pairwise mutually incongruent. So their scales by a are also pairwise mutually incongruent. So if we write down the remainders of these numbers modulo n, they will all be different. They will be pairwise different. So it has some remainder, this has some remainder, this has some remainder, ... So if you write down all the remainders modulo n, we will see n different numbers written over here. But how many different remainders are there modulo n? N. So this set is witnessing all the remainders, all the possible remainders that n has. In particular, it will witness the remainder, it will witness whatever remainder you like. So if b leaves some remainder, just locate just find out what the remainder of b is modulo n. It will be here somewhere in this list. Some member in this list leaves the same remainder as b, because in this list all the remainders modulo n appear. That's it. That is the argument. Okay, just make sure you follow this. It's a very important piece of reasoning in mathematics in general. So fine. So therefore 3 implies 4. 4 implies 5. The remainders of these numbers are all the possible remainders that you can get when you divide something by n in some order. So here, when we write this, when we are writing that the remainders of these numbers are the same as these numbers, we are not saying that a has the remainder 0, 2a has the remainder 1. No. We are trying to say that if you write down the remainders of all these numbers, you will get these numbers in some permuted order possibly. Okay, so using 4, we want to prove 5. Okay. Yeah. So let's see how. Let me think for a moment. Right. So 4 implies 5. So for each by 4 for each, let me add a page, or maybe make it seamless. Yeah. So by 4 for each k in this set, there is, what is the notation? There is some x sub k, some integer x sub k, such that this happens. This is immediate from 4. 4 says that no matter what b you pick, which we are writing k here, there is some x which we are writing as xk, such that this congruence holds, which we have written over here. Right? So for each k you can find an xk. And further we may assume that each xk is of this form. Right? Whatever xk is, whatever number you pick, it will be congruent to one of the numbers here. So the statement that I'm using is the following. For each integer x, there is a unique y in this set such that x is congruent to y modulo n. Very simple, straightforward statement. Think about it. So all I'm saying is whatever xk you found, you just replace it with its counterpart in this range. This equation will still be preserved, of course, because the two things are congruent, right? So I hope this much is clear. It is important that this be clear. So we can assume this. So what do we have? We have this list ax1, ax2, axn, and this list is same as the following list. This list is same as a, 2a, or maybe I'll write a times 2. So this I will write as a times 1, a times n in some order, modulo n. So if I write these numbers modulo n, important, modulo n. In fact, I don't even need to say modulo n. x1 is in which range? In this range. x2 is also in that range, right? So all these numbers, first of all, they leave different remainders modulo n because of this equation. xi and xj cannot leave the same remainder modulo n, right? That's by the choice of xi and xj. So they leave different remainders modulo n. So that shows that xi and xj are pairwise different, right? Even after you constrain them to lie in this range, xi and xj cannot be the same, because were they the same, axi would be congruent to axj modulo n, but that would mean I is congruent to j modulo n, right? So for different I and j, xi and xj are different, right? So the list of numbers x1, x2 up to xn is just a permutation of this list, 1, 2 up to n. Alright? And these leave all the possible remainders that there are, but this list is exactly the same as that list in some order, because x1 is some number in 1 to n, x2 is some number, xn is some number. So these leave all the possible remainders, and this list is same as that list. So they leave all the possible remainders, and that is the conclusion of 5. That the remainders of this list, which is same as that list, are all the possible remainders. So stay on this. This may not be immediately clear as to why, but make sure that you try your best and understand this. It's very important. Okay? I don't want to rehash it. You can pause the video, rewind, and break your head until you get it. Okay, so finally we will be finished if we can show that 5 implies 1. But 5 implies 1 is trivial, because if you have that these leave all the possible remainders, in particular, one of them leaves a remainder of 1. Some guy here leaves the remainder of 1, and that furnishes you the inverse or an inverse of a modulo n. Okay? So that is the end of the proof. So 5 implies 1, I have said it in words, I won't write it. Make sure you get every step in full detail properly. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.